Welcome to Ask and Learn.
In this problem, we have a block A, which is sliding along a surface with a known coefficient of friction. When the block arrives at another block B, which is attached to a spring, it collides with block B and the spring is compressed. We want to calculate the maximum compression of the spring due to the collision. So firstly, we'll look at the principle of work and kinetic energy. So if we refer to the free body diagram of block A, we can see that its weight is acting vertically downwards, and the normal force of the surface on the block is acting in the opposite direction, and there's no vertical motion of this block. There's also a frictional force acting against the motion, which is the coefficient of friction 0.3 times the normal force NA. So let's apply the principle of work and energy. So if we apply the principle of work and energy, we can see first, before we do that, that the normal force must balance the weight, since there's no vertical motion. So that's the mass of the block, 15 kg times g, which is 9.81. And so the normal force is 147.15 newtons. And hence, we can calculate the frictional force. And the frictional force F is equal to mu k times NA. And so this is 0.3 into 147.15. And so the frictional force is 44.145 newtons. Now we can apply the principle of work and energy. So the initial kinetic energy of block A we'll call T1 when it starts its motion 4 meters from block B. This kinetic energy plus the work done U in moving the block to position 2, which is just before the impact with block B, must equal the final kinetic energy of the block T2 just before it strikes block B. So T1 is a half mv squared. That's a half times 15 times its initial velocity of 10 meters per second squared, plus the work done due to friction is the frictional force in the opposite direction, minus 44.145 newtons over the distance of 4 meters. And this must equal to the final kinetic energy just before the collision, a half m VA, we'll call it subscript 1 squared. So if we rearrange this equation, we can find VA1. So the speed of block A is 8.7439 meters per second. And as we look at it, it's to the left. Now that we have this velocity, we can use the conservation of momentum. So we'll use the conservation of linear momentum for blocks A and B. Now we'll take the left direction as positive, and the mass of block A times its initial velocity, which is its momentum, just before the collision, plus the mass of block B times its velocity, must equal the momentum after the collision. That's MA VA2 plus MB VB2. So let's put in our values here. So that's 15 times the initial velocity of block A, which is 8.7439. That's the initial momentum of block A just before the collision, plus 0, since block B is at rest, so it has no velocity. And this is equal to 15 times VA2 plus 10, the mass of block B, times VB2. So simplifying this equation, we get 3 VA2 plus 2 VB2 is equal to 26.2317. And we'll call this equation number 1. So this is an equation with the final velocities of the two blocks, both of which are unknown. So we need to set up another equation. And we'll do this by using the coefficient of restitution. We'll again take the left direction as positive, and we know that the coefficient of restitution given in this problem, E, is equal to VB2 minus VA2 all over VA1 minus VB1. This coefficient of restitution is given as 0.6. And this is equal to VB2 minus VA2, which is still, both of which are still unknown, over 8.7439 minus 0. And so we can again rearrange this equation, and we find that VB2 minus VA2 is equal to 5.2463. And we'll call this equation 2. Now, if we solve these two equations with the same two unknowns, equations 1 and 2 simultaneously, we get VB2 to be 8.3942 meters per second, and that's positive, so that's to the left, and we get VA2 to be 3.1478 meters per second, also positive and also to the left. So we have our final velocities for each block. Now, lastly, we'll apply the conservation of momentum, and this will help us, the conservation of energy rather, and this will help us find the maximum compression of the spring. So remember, B stops momentarily when the compression of the spring is at its maximum. So T2 in this case is 0. So T1 plus V1, this is for block B, is equal to T2 plus V2 when it comes to rest. So after the collision, block B has kinetic energy 1/2 times its mass 10 times its velocity squared 8.3942 squared, plus no elastic potential energy since the spring is unstretched. And this is equal to, comes to rest momentarily, so its kinetic energy is 0, plus 1/2 kx squared. That's 1/2 times the spring constant K, 1000 Newton per meter, times the maximum compression of the spring we'll call X max, and that's squared. So we can make X max the subject of the formula, and we find the maximum compression of the spring to be 0.839 meters.